Okay, so there's another section attached to this. And this we kind of shift gears here. So I'm going to pause real quick and get my applet loaded for rolling dice. Okay, so you can see the probabilities are all kind of approaching that flat distribution, which we expect. So this is a population where all outcomes are equally likely and the probability distribution is uniform. Okay, one of the things I want to show you is that when you increase the sample size, so now I'm rolling 2 dice, there's a theoretical prediction for the outcomes that's triangular. That's if you roll 2 dice. Now, the outcome here is it's computing the average of the 2 dice here. So if I roll 2 dice once and compute the average, it turns out that the average is 3.5. And you can see that the 3.5 is the most probable outcome when you roll 2 dice. And that's just because there's so many ways to get a 3.5. You could get a 6 and a 1, which is 7, divided by 2, 3.5. You know, a 5 and a 2, a 4 and a 3, a 2 and a 4, a 4 and a, you know, and a 3, and it just keeps going on. There's more ways to roll a 7, and when you divide by 2, you get 3.5. So 3.5 is the most common average. If I do this 10,000 times, it's graphing all the different averages here. Eventually, it'll create this triangular distribution of outcomes. Okay, it takes a little while before the theoretical and the simulation line up, but you can see it'll eventually get there. We're over 1,000 rolls of 2 dice. Okay, so these aren't always flat distributions. If you do 2 dice and compute the average, it makes a triangular distribution, sort of a pyramid. Okay, and I think that kind of proves the point. I'll just stop this one. And the activity that I have is to roll 4. Now you can see that when you get to 4, even 3 dice, it's hard to see that there's a bell forming with curvature. The curves really become apparent with 4 dice. So if I roll 4 dice just one time, there's the 4 dice, and the average is down here under run. It looks like the mean is the 3.8 that you see under the M. So that's the mean of 3.8. So it's done one value, and the relative frequency is 100% there because we've only rolled 1. So 100% kind of goes off the chart. It's a really, that red bar goes up real high. But as you do more and more outcomes, then the relative frequencies start coming down because you don't have anything that's 100% anymore. So the probability, you're just dividing up that 100% amongst different outcomes, and the probabilities start getting lower. It's just the average roll on 4 dice. Okay. So what I wanted to do is I'm going to reset this. I don't know, how do I reset it? I think I have to just refresh my page. Okay, so now let's go back to 4 dice. And what I want to do is just do this one at a time and just show how the averages come out. Okay, so I'm going to do one roll of 4 dice, and there they are. The mean is 3.3. Okay, let's just go back over to our tally. This cannot be a 3.3. It's rounding to the nearest tenth. So what they mean is a 3.25. So we'll just go ahead and mark there. Okay. So if it says 3.3, it means 3.25. And if it says, I guess, anything 0.8, it means 0.75. So there's our first one. We're just going to do this over and over. Here's another one. Comes out as a 3.5. So we'll mark the tally there. Okay. It's going to take a long time. 2.3, I'm having questions about doing it this way. 2.3 is really 2.25. Another one. This one comes out as a 5. Wow, okay, so a 5, we'll do a tally. Next one, 5.3. Wow, that's 5.25 actually. Next one is 1.8, a really low one. That's a 1.75. Okay, next one is a 2.8. That's 2.75. Next one is a 3.5. Second one of those. Remember, 3.5 is exactly in the middle between 1 and 6. If you add 1 and 6, you get 7 divided by 2 is 3.5. So 3.5 is going to happen more than anything else eventually. So I got to run it again. Here we go. Next one is 4.3. That's 4.25 actually. Okay, run it again. Next one is 3.0. Okay, run it again. Next one is, oops, it's not scrolling. Here we go. 4.8. That's actually 4.75. Do it again. Okay, this one's a 2.8. 2.75 actually. Okay, run it again. This one's a 3.0. Next one's a 4.5. Next one's a 3.0. So the more common outcomes are the ones in the middle. Okay, next one is a 3.0 again. It's a popular one, almost too popular. Okay, next one, oh my gosh, there's another 3.0. I don't like that. Gotta go with it. Okay, next one's a 3.5. Yeah, I like that one. That's the one that's in the middle. Next one is another 3.5. Okay. Another one comes out as a 4.8. That's extreme. It's actually 4.75, remember. Next is a 2.8. That's actually a 2.75. Do it again. Now I've got a 4. That's extremely high. I'm just going to keep doing this for a bit. Actually, let's do this. Next one's a 3.8, which is 3.75. Yeah, I'm going to run 10 more all at once. Okay, so there they go. And I'm just going to count these in 5. So 3.5, 2.8, 3.3, 4.3. What did I say? I don't think I can do it. 3.5, 2.8, 3.3, 4.3. 3.5, 2.75, 3.3, 4.3. That's 3.25, 4.25. And we do 10 more. Okay. Ooh, except for I forgot the others. That's okay, we'll pick those up as well. So we got the 4.8, 2.5, 3.5, 4.8, 2.5, 3.5. And then there's a 5.3, 2.5, 2.8. 5.3, that's 5.25. 5.3, 2.5, 2.8. That's 2.75. Then continuing back here. So the 3.3, 2.8, 3.3. 2.3, that's the 2.25. Okay. And I'm completely lost at this point. I think that's okay. Let's just go with this. And I don't want to get too carried away with this anyway. So let's talk about our relative frequencies here. All together, let's add this up. We got 1, 2, 2, 6, 5, 3, 6, 1, 1, 2, 1, 3, 1, 2. Okay, and then the relative frequency, we have to add that up. So let's see, 1, 2, 2. And actually, you know what? No, that's okay. Let me do this. 1, 2, 2, 6, 5. Okay, so I got 38 altogether. Nope, I don't think that's right. Just double checking again. Yeah, it's 36. Okay, so then the relative frequencies are all these values divided by 36. So the first one is 1 out of 36, and so on. I don't think I have to graph these though. It looks like I do have to graph them. So we're going to go ahead and make the graph. So all the 1 divided by 36s should be 0.03, we'll just say. I'm rounding that a lot. Okay, so 0.03s on all those. Almost there. Now the 2 divided by 36s, I'm not going to just double this because the rounding may have an effect. So these are 0.06, that's fine. So the 2 out of 36s are all 0.06. Let's do the 3s. So 3 divided by 36 is not 0.09 this time, it's 0.08. There's a 5 divided by 36. So that's 0.14. and then a 6 divided by 36 would be 0.18, I think, 0.17. Okay. So those are our relative frequencies that are supposed to approximate probability in the long run. For 2.75, it should be 6 out of 36. Thanks, Matthew. It's a little, uh-oh. That's okay. So the 2.75 should be 6. And that's going to be 0.17 again. Okay, so there was a mistake there. Okay. So I'll highlight the one that was wrong. Okay. All right, thanks, you guys. All right, so what I want to do at some point is to get a mean out of this. So we're going to have to, well, it looks like we have to graph it first. So let's start with these. So the 1 out of 36 goes with 1.75. Oh, and that's a 0.03, I guess. And I'm just going to draw this one and then copy it to wherever I need to copy it. Okay, so that also goes, 1 out of 36 goes to the 3.75, to the 4, to those. Or more, I think. There was a 4.5 and a 5. And then the 2s out of 36 come next. And the first one goes with 2.25. 2 to 36 better be 0.06. Notability hates me right now. Okay. So that went with 2.25. And Also 2.5, 4.25. Also 5.25. Okay. Four of those. 1, 2, 3, 4, right. Then we have a 5 and 2 6s. So there's a 5 of 0.14 at 3. There's only one 5 and 1 2 6s. The first one's at 2.75. In short runs, these are far from perfect. Best we can do with a short run. So that was 2.75. And then another one at 3.25. Look at 3.5. Okay, so this is trying to look bell-shaped. It's not perfect, but we know in the long run it does go bell-shaped. So this is attempting bell-shape. Okay. But I want to go ahead and pause for a second. Does anybody need a little time? Okay, nobody says any time. Let's go ahead and just do the long run real quick. So the long run, again, I'm going to reset this real quick. I'm asking it to show means. I want 4 dice. These are theoretical probabilities. I'm going to go ahead and do 10,000 rolls of 4 dice. And every time it rolls it, it'll show the average. So let me let that run. We're not going to do all 10,000. But already we're over 200. I think we did 36 individual ones in our little graph. And we just need to understand, to be sort of convinced that it takes a long time. You see I'm over 900 rolls now of 4 dice, and it's still a bit far from the theoretical probabilities, but they are getting closer and closer. I don't think what I really want is for it to give the mean and the standard deviation of all these means. If it doesn't sound like it's going to give us an overall mean, and there's still a little bit of a glitch in the graph with one probability that's kind of low. That's okay. That would eventually make up and get better. But obviously it's going to take a while for those to approach the true long-run probabilities. And my iPad looks like it's stuttering now. It's not going as fast as it was, or maybe it's Zoom. All right, so anyway, I'm going to stop it. We can see that's approaching a bell shape in the long run. So attempting a bell shape long run simulation. Is a nice bell shape. So we know that the probabilities are trying to look normal. Now the mean of the distribution, the applet that I found does not give the mean. So unfortunately, that means we're going to have to we're going to have to compute our own mean based on these 36 rolls of 4 dice. So what we're going to do to get the mean here is we're going to have to put these values in. And you can put the frequencies in or the relative frequencies and you get the same answer. I'll just go ahead and start typing here. So I'm clearing my calculator's memory. And I'm just going to start typing this in under data. You don't have to put all the values in, just where outcomes occurred. So there was a 1.75, 2.25 appeared, 2.5, 2.75, 3, 3.25, 3.5, 3.75, another 4, 4.25, 4.5, 4.75, 5, and 5.25. Okay, so those are the only ones we got. And then you can just put in the frequencies, don't bother with relative frequencies. So the 1.75 had a 1, 2.25 had a 2, 2.5 had a 2, 2.75 had 6, 3 had a 5, 3.25 had 3, 3.5 happened 6 times, 3.75 just once, 4 just once, 4.25 twice, 4.5 once, 4.75 3 times, weirdly, 5 once, 5.25 twice. Okay, so get them all in. And then I'll just go ahead and pop over just to remind you. So all I've done is put in just the outcomes where we actually had data values that were observed. And so these are all the values and their frequencies or relative frequencies, either way, it doesn't matter. And in the end, you hit clear second data. Now the notation it will give, I'm not going to use it, I'm going to change the notation. But the frequencies were in list 2, so you got to change that to list 2, hit enter, and then calculate. Okay, so you see the mean is 3.44 and the standard deviation. Actually, is that what I want? It's a sample standard deviation. Yeah, I think I'll use that. So standard deviation is 0.9. Okay, and what is the population standard deviation? 0.8. Basically the same thing. Okay, that's fine. All right, so let's copy those numbers over. All right, so back in here, yeah, we got sort of a bell-shaped distribution. It's trying. The mean was 3.44. So this is the mean of sample means. 3.44. Okay. Standard deviation, also called standard error, because the sample mean, when it deviates from the population mean, that's an error. So the standard error for standard deviation, I'll call this the estimated standard error. And the mean was also estimated because we're using just a short run to get those estimates. So also the estimated standard error. What I got was 0.9. Okay, but we need to know the mean of all possible sample means if we're going to get, and a standard error. Mostly the standard error, because you have to remember that the standard error in a statistic is just basically two margins of error. I've got that backwards. The margin of error in a statistic is basically two standard errors. Okay, so we have an estimated standard error, but I want the real thing based on long run outcomes, not just 36, if you follow me. Okay, so we have to do a little theory to get better values for this. So I want the mean of all sample means. Okay, so this is going to be mu with a little x bar here. And mean is just another word for expected value. So the expected value of a sample mean is what I mean there. Okay. And now this just uses the properties of expected value and variance now. So expected value of a sample mean, you just have to think about what a sample mean is. It's the sum of a bunch of values x, which are the rolls on the die, divided by n, the sample size. Okay. Now, I wonder, there's a list of rules. I wonder if I should put them down somewhere. I'm going to go down to the corner here. The rules were that the expected value of kx is k times the expected value of x. Okay. The expected value of x plus y is the expected value of x plus the expected value of y. Those are the only ones I need right now. Okay, so here I'm going to bring that k, which is the sample size. Well, 1 over n is my k, bringing it up, times the expected value of the sum of my values, okay, or the sum of my x's here. Okay, but remember the expected value of a sum is the sum of expected values. So this is 1 over n times the sum of the expected value for each roll of the die. Okay. The expected value of x goes back to the actual individual rolls on a die. X was 1 roll, and the expected value, mu, is e of x. Okay. So that's going to be just 3.5. So going back, we can say that's the sum of the expected values of x. Again, 1 over n. The sum, the expected value of x is the mean of the original population. And if you're adding the n of these together, then you're going to have n times the mean. Okay? But the n's cancel, and you just get the mean. Okay? So the mean of all sample means is the mean of the population you're sampling from. So step back, remember we got 3.44 as the mean of all the sample means. That's approximately 3.5, and it would have been 3.5 in the long run. Okay, we only did the short run on this, and we got 3.44, which is pretty close to 3.5. Remember, the 3.5 was at the beginning the average roll on one die. 3.5. But if you do the average of all averages from 4 dice, you should get, this thing says you should get, we got a 3.44, but in the long run, you get a 3.5. And that's what the central limit theorem says. It says the mean of the sample means is the mean of the population you're sampling from. Okay. So that's great. But then more importantly almost is the standard error, because that'll give us a margin for error. So we'll go ahead and put this down, standard error. Oh wait, I gotta erase that. We have to do variance first. Variances are always how you work with standard deviations first. So the variance of all sample means okay. So this is just var of x bar. X bar is a sample mean. Okay. And I do the same thing here. I'll say, oh, well, that's the variance of what x bar is, where x sample mean you used to add up your outcomes and you divide by your sample size. And now I need principles again. Okay, now this assumes that the variables are independent. So if each outcome is independent, I'll just say in depth, then we know that the variance of x plus y is the variance of x plus the variance of y. Okay. Independent just means that the dice aren't influencing each other as they roll. I think that's a fair assumption. And then also the variance of kx is k squared times the variance of x. It's been a while since we saw that. Okay, so that sum of x over n, I'm thinking as a 1 over n as my k. But if I bring it out, it becomes a 1 over n squared. Okay, and then you have the variance of the sum of each outcome. And the variance of a sum is the sum of the variances. That's the second to last rule here. That's if the rolls are independent of each other. So variance of the sum is the sum of the variances. I have 1 over n squared times the sum of the variances, which is var of x. Okay. The variance of the variable is the square of the standard deviation. So that's 1 over n squared times the sum of sigma squared. That's just what variance is this square of the standard deviation. And if you add the standard deviation to itself, sorry, the variance to itself n times, that's just n times the variance. So this is 1 over n squared times n times the variance. And of course, that simplifies as just sigma squared over n. I'm having a little trouble with it. Okay, any questions? Now, variance is only important really so that we can get the standard deviation. So the variance of sample means is the square of the standard deviation. So let's do this, the standard deviation or error of all sample means the symbol is sigma x bar. So it's the standard deviation of the sample means, which are all x bar. But standard deviation is the square root of variance. So I say, okay, so this is the square root of the variance of x bar. Okay. And we did that. This is the square root of sigma squared over n. So square root of sigma squared is just sigma. So you can write this as sigma over the square root of n. All right, so that's a really important formula because that's the standard error. And remember, the margin of error is usually 2 of those. So when we do the margin of error for an average, it's just going to be approximately 2 standard errors. So now we've got a formula for the standard error. Okay, any questions about that? I'm going to put a box around that so it doesn't get confused with the other stuff. Okay, so that's all just sort of theoretical. I wonder if I am ever, do they match? Okay, yeah. We'll run the formulas in a sec. Okay, so there's a big theorem down here that's pretty much summarized by 3 important ideas. The first idea is that the means come out with a bell-shaped distribution. And I should say, this is still not as bell-shaped as it could be. You can see as I increase the sample size, this begins to look more and more like one of these beautiful normal curves. And of course, you don't, these are theoretical distributions that I'm showing. But if you do this long run, here I'm rolling 10 dice, and we're just saying that this distribution becomes more and more like that perfect bell shape. And this is really the importance of the normal distribution. We can't control the distribution of a random variable. It is what it is. So the role of a die, just one die, the variable being the roll, we originally said, oh, that's a uniform flat distribution because every roll has the same probability. So that variable does not have a normal distribution. It's a uniform distribution. But if you roll 10 dice, like I'm doing here, and work with the average roll, you get all kinds of averages. But the averages themselves, while the dice don't have a normal distribution, the average roll has a normal distribution. And again, that's the importance of the normal distribution. It's not really that lots of things out there have normal distributions. The important thing on the normal distribution is, regardless of the population you're working with, when you do averages from that population, they will come out with a normal distribution as long as your sample size is big enough. I don't know if you remember when I did sample, this is coming out bell-shaped, right? So we'll stop that. But when you do samples of size 2, that's not normal. That's just this weird kind of pyramid rectangle thing. Okay, it's the increasing sample sizes that bring about the normality. Okay, and so that's the importance. We're going to have a rule about how big the sample size needs to be. Okay, but eventually, you know that the averages come out with a bell-shaped distribution, and that's why the normal distribution is so important. Okay. So that all of that kind of summarized. There's a rule that the rule is that you have to have samples of size 30. Okay, so from any population, with mean mu, and standard deviation, sigma, consider the population of all possible sample means which are x bar from samples of size n. Okay, and then in parentheses, we'll say this is the sampling distribution of sample means. Um, this distribution has mean mu with an x bar subscript because it's a mean of sample means, and standard deviation or standard error, sigma x bar. Okay. The following can all be proven. Now I've proven 2 things out of 3 here, and the third we've suggested with simulations, but it can also be proven, but the math is really hard. Okay, the first thing that's the hard thing is that the population of sample means, the distribution of sample means approaches normality with increasing sample size. And the rule is it needs to be bigger than 30. Or your population has to be normal. So let's say the distribution of sample means of sample means, we say normal, but we only ever mean approximately normal. If the population we are sampling from is normal, or the sample size is bigger than 30, let's go ahead and put that in first. If n is bigger than 30, that's our rule. The real rule, I'm kind of fudging a little bit. I'm giving you the rule of thumb right now. The theorem just says with increasing sample size, the sample means approach normality. But almost all statisticians go with the greater than 30 rule. So the distribution of sample means is approximately normal if n is bigger than 30, or if the population we're sampling from is normal. And I've been through the proofs of this with maybe an hour of preparation. I could prove it, but it's really hard, and it requires calculus, so that's kind of an issue. But calculus and a good background in statistics to learn about some of the difficult topics like moment generation, moment generating functions and stuff like that. It's really crazy stuff. Okay, and then we learned that the mean of sample means is the mean of the population we're sampling from. That was up above. We did this proof. I may be frozen. That's frozen. Oop, there it goes. Okay, so we had the mean of sample means right up at the top here equal to the mean of population, and the standard error of the sample means was sigma over the square root of n. So we'll put that all down here. Okay, so for the dice rolling, the mean of sample means is the mean of the population. I don't know if you remember, that's 3.5. Okay, in the simulation, this gave a 3.44, which is close. Okay, just off by less than a tenth. The standard deviation of sample means is sigma over the square root of n. Oops. So sigma, we have to go back way to the top, and we're looking at the population we were sampling from, which was the rolls on a die, the mean was 3.5, the standard deviation was 1.7078. Okay. And this thing is saying that that standard deviation, the standard deviation of the sample means, would be the standard deviation of the population, 1.7078, over the square root of our sample size. Remember, we were rolling 4 dice, so it'll be over the square root of 4. So you just do 1.7078 divided by 2. 1.7078 divided by 2 is going to be 0.85, which is approximately 0.9. The simulation would be 0.9. And it's under no obligation to follow theory, but it does. Okay? In the long run, the simulation will approach 0.9, and the mean will approach 3. The mean will approach 3.5. Okay. Now remember, for the margin of error, I just want to kind of slide back to 7.2 real quick. So just one moment while I bring up 7.2. Down at the bottom in 7.2, we learned that the margin of error was this z alpha over 2 times this standard deviation, which is called standard error. Okay, that's just the standard error of our statistic, and it requires that the statistic be normally distributed. Okay, so if you go back to where we are now, we'll say the same thing. The margin of error is z alpha over 2 times the standard error, which is sigma, not p hat, like it was in just a second ago. This is the standard deviation of sample means. So again, we use the z alpha over 2. It assumes normality because we use the bell curve to get this value. Okay, and then the sigma x bar, that's the standard error. So in the end, we're going to go z alpha over 2 times sigma divided by the square root of n. Okay, and that's our margin of error for a sample mean. Okay, so I know we already took a break, but I'm ready for another one. So let's take a 5-minute break.